Greetings, students. Welcome to this week's lab. We are going to be investigating the San Andreas Fault and plate tectonic theory. You've probably heard about the San Andreas Fault all of your life if you've lived in California. And if you haven't lived here, then maybe you just knew it was something to be scared of. Today I'm going to do my best to demystify the movements along this fault. There is a reason to be wary of this neighbor of ours, though. I first want to revisit something we talked about a couple of weeks ago. This is the concept of the hypothesis and the theory. Remember that when people say in everyday life that they have a theory, what they really mean is that they have a hypothesis. They have a hunch as to why something happens. But in science, a theory is not a hunch. University of California Museum of Paleontology at Berkeley defines theory as a broad, natural explanation for a wide range of phenomena. Theories are concise, coherent, systematic, predictive, and broadly applicable, often integrating and generalizing many hypotheses. Any scientific theory must be based on a careful and rational examination of facts. Facts and theories are two different things. Facts can be observed and/or measured directly or by proxy, and theories are explanations and interpretation of the facts. A good theory is developed from several hypotheses that have been tested and retested by multiple scientists. And theories aren't the end-all be-all in science. They can be rejected. Why? As more information, data, facts is gathered over time, the accuracy of the explanation improves. Remember that, in general, a hypothesis is an if-then statement that can be tested and retested. It is something that can be supported or refuted through experimentation or observation. I'm sure you're now asking, okay, what's a law then? Some mistakenly believe that a theory becomes a law, but this is not the case. A law is a description of an observed phenomenon in the natural world that holds true every time it is tested. Theories are used to explain the laws. A nice little video on this is found in the supplementary information for this slide. The PowerPoint is found in the folder online for this lab. I bring all of this up because the explanation of how the San Andreas Fault works is within the framework of plate tectonics theory. Here is a Google Earth image of the many faults in the western United States. The red line is the San Andreas Fault. The green lines are other fault zones. CSUSB is labeled. Notice how it is on the southern section of the San Andreas Fault. Do you see how the San Andreas Fault is much longer than the other faults? That is because the San Andreas Fault is also a plate boundary. Recall that the Earth's crust is broken into plates that move relative to one another. Some plates crash into each other, other plates move away from each other, and other plates slide past each other. It is along these plate boundaries where we find the majority of earthquakes, volcanoes, and mountain building events. The San Andreas Fault is the boundary between two plates, the North American plate and the Pacific plate, that are sliding past each other. There is no volcanoes that form at this type of plate boundary, but there certainly are earthquakes. Here is a close-up of the southern section of the San Andreas Fault. You see the Salton Sea to the south and the Garlock Fault to the north. The Garlock Fault marks the northern boundary of the Mojave Desert. The San Andreas Fault actually ends at the Salton Sea, but the boundary between the Pacific Plate and the North American Plate extends south into the Gulf of California, also known as the Sea of Cortez. In the map on the left, you see our Cal State San Bernardino campus and a golden line to the northeast of campus. This line marks the boundary of the Pacific and North American plates. It is the San Andreas Fault, and yes, it is very close to campus. Usually we hike there during lab. It's just about a mile up from the campus. In the PowerPoint uploaded online, you will find a supplemental video in the slide notes. This is a video that was done by a colleague of mine. He created it so that people could go on a hike virtually if the lab class met at night or if the weather was poor. For now, though, I'll lead you through pictures. We do this hike to investigate evidence of movement along the San Andreas Fault. If there is movement along the fault, then we should find evidence for that movement. And indeed, we see some interesting things in the rocks back there. One bit of evidence for the existence of a fault behind school is that there is a mismatch of rocks. There are sedimentary rocks that have been moved laterally to be in contact with igneous rocks. These sedimentary rocks were offset from a different locality along the fault and are now juxtaposed next to this igneous rock. In this Google Earth image, we see more evidence for the existence of the San Andreas Fault. A stream channel noted by the blue line with the number 1 next to it sits in Badger Canyon. Notice that there are two well-established river cuts that are to the left of the mouth of Badger Canyon. These are labeled 2 and 3. At one point in time, Channel 1 was connected to Channel 3, but over time, the channel on the northeast side of the fault moved to the right relative to Channel 3. Channel 1 was cutting a new channel, which is Channel 2. But Channel 1 moved laterally to the right again. This is definitely evidence that there is lateral movement along the fault. And we can see from this that the San Andreas Fault displays right lateral movement because if we stand on this side of the fault and look to the other side moves to the right. If we stood on the other side of the fault in Channel 1 in Badger Canyon and looked back this way, which way would the channels 2 and 3 have moved relatively? That's correct, to the right. This is a right lateral strike-slip fault. More evidence of the existence of a fault is that there is a line of trees along the fault. This indicates that there are springs in the area that come up along the fault. The rock in the fault zone is often ground up, making it easier for water to percolate up to the surface. Even during the summer, you will find a line of trees here at the fault. Maybe you have heard of Arrowhead Springs water. This water comes from a spring in the San Bernardino Mountains. The area behind campus is actually the San Andreas Fault Zone. One of the faults in this zone that splits off from the San Andreas Fault is called the Mill Creek Fault. This fault could be traced over to Waterman Canyon, and you will find Arrowhead Springs. That is the better known part of this spring system. One more line of evidence I want to show you can be seen on this trail. You can't really see it in this image, but if you were hiking out there, you would notice that it is a rather gradual incline to the fault, and then suddenly it gets steep right near the fault. This steep section is called a fault scarp, and it is probably created the last time this area ruptured in 1812. Along the fault scarp, the rocks look all ground up. This makes sense. If the plates of solid rock are going to grind up against each other, then rocks are going to be broken. This is called fault breccia. In this area, the brecciated rock forms a zone about 100 meters wide. This suggests that there is a long history of fault movement to ground up so much rock. In your lab manual, there are more thorough explanations of what I have described, so please go there to read more about these features. In the next part of the lab, you will be calculating slip rates and recurrence intervals. In this first example, you are given information about the fault. Survey measurements show that the region around the strike-slip fault is bending at a rate of 10 millimeters per year. The most recent earthquake on the fault occurred in the year 1900. During that earthquake, the two sides of the fault slid past each other by 2 meters. If the fault were to slip again tomorrow, how far would you expect these two sides to slide past each other? Distance equals rate times time. So 10 millimeters per year times 120 years equals 1,200 millimeters, or 1.20 meters. Another thing you'll be asked to calculate is the recurrence interval. It is also known as the average time between earthquakes. Here is an example. If a fault has 6 earthquakes in the last 6,000 years, what is the recurrence interval? Using the equation Ri equals time divided by the number of earthquakes, you see that 6,000 years divided by 6 earthquakes equals a recurrence interval of 1,000 years. That would be the average time between earthquakes. Please take note. You will need to show your work for the problems in this lab. Make sure to scan your work and upload it to the correct location on the quiz. The work must be handwritten and not typed. The recurrence interval on the San Andreas Fault is 200 years. The last time there was a major earthquake local to CSUSB was in 1812. The epicenter was in Wrightwood, California. If the recurrence interval is 200 years and the last one was in 1812, then we should have had one in 2012. if you look at the averages. We are overdue. This map shows localities where data has been collected about past earthquakes. The 1812 earthquake was responsible for damage to many missions and other adobe structures from the San Juan Capistrano to Santa Barbara areas. Another thing to notice is that on the southern section of the San Andreas Fault, the last known earthquake was in the 1600s. We are overdue for an earthquake in that region for sure. In your lecture, you will learn more about the mechanisms of faults and why they stick and then slip. In the next few minutes here, I would like to review some concepts that relate to plate tectonics. First, plate tectonic theory is very young. It has only been around since the 1960s. Before that, most geologists thought that ocean basins were very old and that continents were fixed in one place. Those ideas were discarded, though, as multiple lines of evidence started to point towards plate tectonics. Plate tectonics is the foundation of modern Earth science. It was Alfred Wegener who formulated the idea of continental drift. He collected evidence that led him to hypothesize that the continents were not in fixed positions and they were actually slowly moving over geologic time. In fact, he said that they drifted apart from a supercontinent that had existed, Pangaea, about 200 million years ago. Wegener's evidence that Pangaea existed but later broke into pieces that drifted apart included the puzzle-like fit of the continental margins, continental fossil organisms that matched across oceans, matching rock types and mountain belts, and sedimentary rocks that recorded ancient climate regions. There was a great debate regarding this because Wegener could not provide the mechanism for how the continents drifted to their current localities. His hypothesis was disregarded for 50 years. Research conducted during World War II started to breathe new life into Wegener's hypothesis. Marie Tharp overcame sexism against female scientists to create the first scientific maps of the ocean floor using data collected during World War II from Allied ships who scanned the oceans for German U-boats. She worked at the Lamont Doherty Earth Observatory with Bruce Heezen and continued to work with grad students in the years to come. The maps she developed revealed the very topography of the ocean floor, including the existence of a long ridge system in the middle of all the oceans. Subsequent sampling of the ocean crust showed that it was much younger than previously thought relative to the continents. This work led to the understanding that continents do drift because the seafloor is spreading in certain areas. How continental drift and seafloor spreading work together is all part of the plate tectonic theory, where the crust of the Earth is divided into different plates. These plates move relative to one another. There are parts of the Earth's crust that are thin but very dense, and other parts of the crust that are thick but less dense. The thin, dense crust is known as oceanic crust. It is thin, about 5 to 8 kilometers thick, and dense, about 3.2 grams per centimeters cubed. Note, water has a density of 1 gram per centimeter cubed. Oceanic crust is mainly composed of a rock named basalt. This is the type of rock you imagine when you think of lava rocks. They are dense because iron and magnesium are abundant chemical components. Continental crust is less dense, about 2.7 grams per centimeters cubed, but much thicker at a 40-kilometer average. Continental crust is composed mainly of granite. This is the light-colored rock you often see if you hike almost anywhere in our California mountains. There are 7 large plates and many other smaller microplates. Most plates are composed of both oceanic and continental crust, though there are a few plates that are composed of only oceanic crust. Plates move relative to each other at their edges. These edges are called plate boundaries. Plates meet along boundaries that may either be divergent, where new crust is being created as the plates split apart from one another, or they can be convergent, where plates can come together. Because there is 2 different types of crust, there are 3 different types of convergent plate boundaries. Oceanic crust converging with oceanic crust converging with continental crust, and continental crust converging with continental crust. In the first two iterations, volcanoes are created, where the denser crust is subducting beneath the less dense crust. Volcanoes form on the abducting crust above the subduction zone. Where continental crust converges with continental crust, there is no subduction zone, and instead, the tallest mountains in the world are formed. The third type of plate boundary is a transform plate boundary, where crust is moving laterally past each other. Most transform plate boundaries are found connecting sections of the mid-ocean ridges in the oceanic crust. On occasion, you will find a very long transform plate boundary in continental crust. The Alpine Fault in New Zealand is one of these boundaries, and our very own San Andreas Fault is another transform boundary that cuts through continental crust. That brings us full circle and back to the San Andreas Fault. This introduction has prepared you to answer the questions for today's lab. There is also information in your lab manual and in your lecture textbook if you need clarification. I posted the lab manual online for you to use. The questions you will answer are found on Blackboard. The online quiz is also found in the same folder. Make sure to submit the lab on time. Please make sure to read your announcements and follow any and all directions about the assignment. Make it a great week, and I'll see you soon.